start the session?
Yeah, please go ahead. Start the session.
Yes, sir. Now we are live in both YouTube and the Zoom, sir. And you can start the session. And I
Okay.
checked the Google forum and there is no more questions, sir.
Yeah, so questions will be posted here in this
Chat box, and they will come in Zoom. They can come through video also, sir, and they can speak. In
yeah,
YouTube,
but
if any questions comes,
if
I
somebody
copy
wants to
paste.
write, they can write here, no?
Yes, sir. In chat box, they can write.
There is a chat box, no?
Yes, sir. If anybody asks question in YouTube, I'll copy the question and paste it here in the chat box.
Right, right.
Over
Perfect.
to you, sir.
Yeah. So I welcome you one more time to this live session, and what we are trying to do in this course, particularly we are trying to, it is more like clarifying few fundamental points associated with quantum dynamics. The first thing I think this is, I'd like to share this screen. Everybody can see the screen, no? All of you can see the screen?
Yes, sir.
Yeah.
Yes,
Okay.
sir.
So of course this is a session when where you can ask question directly, and I'm here to clarify doubts you have. Huh? So you please go ahead, feel free, and I will try to clarify. It's a complicated subject, and I think the percentage, let's say 1% of entire quantum dynamics problem we are addressing right now, it's a very little percent, but that little percent is very important to begin with. To have this idea, the moment you clarify these fundamental ideas, you'll be able to extend this idea for more complicated system. So one thing which we should remember is that in quantum dynamics, with this very colorful distribution functions at different time, what I have shown, this is the actual representation of quantum dynamics, where distribution function itself is evolving as a function of time. And distribution function, it means it's spread out in space. So in the x-axis, you can see everything is spread out. So does it mean that the size of the particle is like that, like a dinosaur? No, size of the particle is still a quantum particle because it is quantum. It's so small. That's why this quantum effect is showing up. And a quantum particle is a point particle, let's say. It is staying at a particular point. But the problem is that we won't be able to identify where it is. So this picture, what I have shown, is just before the measurement. I haven't done any measurement. And this is a dichotomy. This is a duality. Many occasions we get confused. So before the measurement, how do I know this is the distribution, right? I'm not measuring it. So if I'm not measuring it, I don't know what does it mean. Okay, so this dichotomy is there, and I think this topic is discussed, particularly this kind of before measurement and after measurement picture is discussed in the context of quantum computing. One of my students has taken interest recently, and that's why I'm going through those aspects. Very interesting. Anyway, so the whole idea is that before measurement, this entire thing is evolving just like the way I have shown here, all these colors. Distribution function is evolving. So what does it mean if I do the measurement? If I do the measurement at a particular point, at a particular point of time, I will get a single point. Let's say a point, I will draw it here, a point like this, a single point. Although this doesn't look like a point particle. It has a big width, but let's consider it's a very point, a tiny little particle. Okay, so if I do a measurement, I'll be able to find out a single point. Now, where the point is going to be in the next measurement, if I do, it is not necessary that the point would be at that point only, the previous point. It can be somewhere else. But overall, all the points which I'll get experimentally, they will be within the distribution function. That's the whole idea. So in the most confusing part of quantum dynamics is that you are not dealing with a single particle actually. You are dealing with an ensemble. Okay, but still you are thinking about the group, right? But still you are finally drawing conclusion for a single particle. Okay, so I will stop lecturing right now because every NPTEL video I have been doing it. It's a slow lecturing, and I would like to hear from you. I will go one by one. I'll stop sharing it first. No, this is in. How do I stop sharing? Stop share, yeah. Yeah. So I can go one by one. Whoever has joined, I think few participants have joined already.
Sir.
Yeah, who is?
Sir, I had asked one question in. Sir, myself Sandeep Kumar, sir.
Sandeep, you directly asked me the question. Yeah. Sandeep,
Yes, sir.
First, you introduce yourself, where you are working, and.
Sir, myself is Sandeep Kumar, sir. Actually, I passed out from IIT Kharagpur, sir, and after that I have worked in some industries, sir. But as an amateur, yes, sir. As an amateur learner, I'm new to this course, sir. So I want to learn something, sir.
Yeah, very good. Yeah.
So, sir, one question I had in that Google form, sir, that it is regarding the it is regarding the module 3, lecture 17. Sir, in that you actually derived the phase velocity for a free particle, sir. And the expression was h cross k upon 2m. And the group velocity was h cross k upon m. M, sir. And here the actually the group velocity is matching with that actual particle velocity, sir.
Yeah, but what is actual particle velocity? Is it?
Yes, sir. Yes, particle velocity is that h cross k by m, sir. H cross k by m.
Now, particle velocity, Sandeep, when you say particle velocity, what does it mean, particle velocity? Is it, either you are saying classical velocity?
Yes, sir. Yes, sir. Classical velocity.
Classical velocity, yeah.
Yes, sir. So, sir, in that case, you said, sir, that actually phase velocity should be more than the group velocity, sir. But in this case here, sir, the phase velocity is less than the group velocity, sir.
Why do you think that phase velocity should be greater than the group velocity?
Sir, because that is actually the fast varying component. It is carried by the carrier wave, sir.
Yeah.
The phase velocity part is carried by the carrier wave, and that part is the fast moving component. So it should be more.
Okay. No. Velocity, yeah. That's a good. I see what you are saying. That is the. Yeah, that's a good point you have. I mean, really, you have thought of it. So you see my hand?
Yes, sir. Yes.
Okay. So the whole idea of this group velocity and phase velocity, think about the light. Light is better to do with. So this fingers are representing those very fast varying component. Okay, and this tip is representing the envelope. So these two together is representing what you have in the web packet or a pulse, okay, optical pulse. Now, now it may so happen that this one, when it's propagating, they can be locked, okay, which means that phase velocity and group velocity equal. But that doesn't happen for wave packet, the particle wave. So for particle wave, group velocity would be faster than the phase velocity, which means that when it's propagating, it will be moving, it will be, so both are propagating, but when they're propagating slowly, this is going to happen. See, this part will be happening like this. So this part is moving faster than this part, right? And that is going to happen. Now, the fast varying component, if you think about the fast varying component, that has a frequency, let's say, much higher than the variation frequency. So how do you define the velocity? Sandeep, how do you define the velocity? We have given the definition of the velocity all the time.
Yes, sir.
What is the definition?
Yes, sir. Yes, omega by k, na sir. Omega by k.
Yeah, but how do you get that? It depends on, you take the total phase. So phase has the entire information hidden in it, right? So you take phase, and then you are trying to find out how quickly the same phase is repeating, which means that you take the first derivative of that phase with respect to time and make it 0, right? If it is propagating like this way, then phase is repeating, no? Here is repeating, here is repeating, here is repeating. So this repeated phase, the say constant phase front, how fast this constant phase front is propagating, that is the phase velocity, right?
Yes.
So phase velocity, it directly does not depend on the frequency. It is actually the ratio, right?
Yes, sir.
It has a k contribution as well. So
yes,
think of in terms of how quickly it's, so the place where you are getting confused is that because it is fast varying component, fast varying in terms of frequency.
Okay, sir. Okay, sir.
Okay. But then total phase, the velocity of the constant phase front can actually differ. It is the constant phase front, how it's propagating. So that can differ. Okay.
Okay, sir. Okay. Okay, sir. It means it is actually related to frequency, sir.
It is
that faster and slower part is related to frequency.
Frequency, exactly. And but the velocity depends on the phase, total phase. And total phase has both frequency contribution as well as the k contribution. See, omega t plus kx or minus kx, whatever. So total contribution is going to affect the velocity. So it may, so here look at this, my fingers and this envelope part, they can be locked. So same velocity, I can have faster than this. So when it's moving, you see how fingers are changing, and they can be slower than one another. So like this. You're following it?
Yes, sir.
Yeah. So
Okay.
what is going to control it? What is the phase it has? Okay, and the second thing is that group velocity. You have to remember that group velocity is not just the phase. It's just not depend on omega. Group velocity is the derivative of omega.
Yes, sir.
Right? So
Yes,
these
sir.
two
D
are
omega by
making
2.
difference. Yeah. Just don't think about only frequency. It is something else. In addition to the frequency, there are something else also combined together jointly. They have the display of velocity.
Yes, sir.
Okay.
Okay, sir.
Okay. We have another question. Jutan, right? Is it Jutan? I have a physics article I want to share with you. Okay. Jutan, can you ask the question directly here? Jutan? But this, yeah, I mean, let him come back. I think somehow I don't hear him. But Sandeep, what you have done actually, you have started thinking of it, and that's very important. Huh?
Yes, sir.
Otherwise, the entire subject is going to be a mathematical subject. It is not a mathematical subject. As long as it is becoming a mathematical subject, you will not get the test.
Yes, sir.
But more you think of it, more you try to visualize, which is very, very difficult. Classical,
Yes.
you can visualize many things, but quantum mechanically, the meaning of it, its visualization becomes extremely difficult.
Yes.
And think of it. Huh? I often give this example when I say chicken tikka masala. You know what does it mean, right? In front of your eye, you can see those gravy and then chicken. But if I say that probability density distribution, what does it mean? Similar visual perspective should be in front of you, right? And that can be developed just by thinking. More you think of it. Uh, Lecture notes are given, presentations are given. What you need to do is just think. Don't need to memorize anything.
Yes, sir. Sir, I have one more question, sir.
Yeah, tell me.
Sir, regarding the superposition of waves, sir, in the actually in the module 1, sir, it is by the superposition of two waves, sir. You actually derive the time period of that oscillation, sir, oscillating part. Oscillating part was coming h by delta E, where delta E was the energy level of two different energy levels, sir.
Right.
And that example you also showed via the harmonic oscillator as well as that the hydrogen molecule example, sir.
Right.
So yes, sir, H2 problem. So sir, there, sir, that time period h by delta E, sir, it has formed very similar to the Heisenberg uncertainty principle, sir. That time is h by delta E. So, is there any relation between this lifetime, sir, and Heisenberg uncertainty principle? Because it is
portraying that
time
sense
taken for the transfer of electron distribution.
Right. It is trying to portray the same sense, actually. If your energy difference is very long, very large, if the energy separation is very large, then time period will be very small. If the energy separation is very small, then the time period of this oscillation would be longer. So it is carrying the sense, right? The texture of Heisenberg uncertainty principle, that texture is actually hidden in this expression. But yeah.
Yes. Okay. Okay, sir. One more question, sir. One more question I have. Sir, you actually represented one particle via a matter wave, sir. Matter wave. So a matter wave, sir. In order to form a wave packet for a particle, you took two different k values, sir. K value as well as different energy values.
Right.
And these two you superimpose, sir, and made a wave packet, sir. Wave packet.
Right.
So it means that particle is having two different k as well as two different energy levels, sir.
Yeah.
So, sir, whether this different k is from the Heisenberg uncertainty principle, because momentum is related to h cross k, sir.
Yeah.
That h cross k, na? So their k terms comes, and also for energy part, that p part comes, sir. That momentum. Sir, so for making that wave, sir, that particle representation of a matter wave, we are taking different components of k as well as different energy, and then we are superimposing, and actually we are forming a matter wave. So that matter wave is also having uncertainty, sir.
Yeah.
Sir. So whether this uncertainty is coming from Heisenberg or this actual matter wave is giving Heisenberg, sir?
No. Every whatever uncertainty you are saying, that idea always has a single origin. That is the Heisenberg uncertainty principle. But you can realize, see, Heisenberg uncertainty principle is a particular, let's say a particular, how should I say, a theory, let's say, and a very important theory in quantum mechanics. But you can reach that conclusion from different points of view. So what you can do is that when you do the superposition and all these things, you are reaching the similar conclusion, right? So you are actually...
Sir.
Yeah.
Yes, sir. Actually, you are taking two different k values, na, sir? Nearly close k values. From where you are getting those two k values, sir?
Yeah, I got your idea. So you are thinking that if I have a particle, it should have a single k, right? That is your first hypothesis, and based on that hypothesis, now questioning. Am I right, Sandeep?
Yes, sir. Yes. Yes, okay. Sir.
That is a problem. That hypothesis is wrong. See, if I have a particle, a tiny little particle, hydrogen atom, electron, I have captured one electron in this fingertip, let's say. Okay. This electron, because I have localized here in this space, not in Delhi, not in Kolkata, not in somewhere else. In Bangalore, I have localized it. Because I have localized it, it means that this electron does not have a single K. Okay?
Yes, sir.
Single K, it means that single energy. Energy is what? Electron cannot have vibration, rotation. It has only translation. So kinetic energy. So I'm saying that I'm holding one electron in my fingertip in this space. Okay? But it has kinetic energy, definite kinetic energy, E. That is wrong. I cannot have a localized electron with definite kinetic energy. It is not possible. Okay, so your view is let's say I have a ball. This ball is moving with a particular velocity. Similarly, one electron particle should move. Okay, when it's moving, it should have a single velocity. No, it has a group velocity. So imagine when I'm holding this tiny little electron particle, I'm actually bringing all the energy levels of that electron, free electron, and making a superposition, bringing them in superposition, and then I'll be able to hold it. Otherwise, I'll not be able to hold it. Okay. So
yes, sir. It means for making that whole matter wave Sir, in order to make the matter wave, means in order to make the superposition, we require those wave functions, sir.
Yeah.
So from where we are getting the actual wave function, sir? What is the source of those wave functions? Because we should take certain close values. So what are those close values, sir? So how we are selecting those values, sir? Those my question.
It depends on the superposition, this. So this is your x-axis. On this x-axis, you have localized the particle, which means you have localized the wave packet here. If you have localized here, in order to localize within this space, this width has an information of space. So similarly, in order to have this little width in space, you need a width in k. So position space and momentum space is correlated. So how many such k you need, what are the k's you need, that depends on this conversion, right? If you do the Fourier transform of this position space, this width, you'll be able to get a width. This is your k axis now in the k domain. And on the k domain, you have another width, right? So this distribution function is showing that
Yes.
what are the k you need. You following me? And those
Yes.
are nothing but
Yes,
the
sir, yes.
solution of the free particle. If you get the free particle solution, which is the plane wave, those solutions, which is going to be continuous, okay, you need those k's only. So depends on how you are going to localize,
Yes.
localize it. The moment you have that information that this is localized here, then in order to localize in this place, how many and what kind of k you need, that information will come from the k domain information.
Yes. Yes, sir.
Okay, you're really thinking. I'm really happy to
Yes.
you. It is really a pleasure to talk to you, Sandeep.
Yes. Thank you, sir. Thank you.
Yeah. Jutan, you have any question? I think you said that, can you share me your email address? Oh, I see. Okay. Okay. I have a physics article I want to share with you. Okay. Think of it, huh? Sandeep, think of it. And this is not the end of the discussion. We should continue the discussion. So you are
Yes.
in industry right now?
Sir, I was just at the time of Corona, I left one industry, sir. Now at present, I'm not doing, sir. I'm thinking of.
Okay. You are working in the industry. I didn't hear. You are working in the industry right now?
No, sir. Just I quit, sir. Just I quit. So
I see.
at present, I'm not working. So,
Okay,
but I'm
no
thinking
problem.
that if possible, I will go for.
No problem. I mean, good to hear that somebody coming from industry background is taking interest in quantum thing. And right now, quantum computing is something which industry is taking interest in. So, and quantum computing is all about the superposition. Whatever you have studied in the first lecture, whatever I have presented, that is the basic starting point of quantum computing. Okay. Anyway, we have another.
Yes.
Sarika has requested for the soft copy of the David Tanner book. Sarika, I'll see what can be done. This is a. Okay, I may have personal copy. Okay, so do one thing, Sarika. You write to me. I will be able to help you. Please write an email to me. This is my email address. Write to me. I will help you. And I don't know. Jutan is not responding. he wants to share one article. Okay, let me ask the other question. We have another member here, Gracie. Gracie, can you hear me? We cannot hear you, Gracie. Although seems to me you are trying to, you have to unmute yourself. Yeah, unmute. This online thing is very annoying. I don't like this one. Yeah. Now can you, Gracie, can you talk? We cannot hear you. No, we cannot hear you. Do one thing. You ask. Yeah, good. Yeah, okay, fine. You have a problem with mic. Ask one question. Anything you like. One question, because you are attending this.
Hello.
Yeah, I can hear you now.
Okay. Good evening, sir. Sorry, there seemed to be some problem with my mic. So, sir, yeah, I've been meaning to ask you a question. We were discussing about the normalized. Sorry, before that, my introduction. I am Gracie Sharma. I'm currently pursuing my master's in chemistry from Central University of Punjab. I'm in my first semester right now. So,
Okay.
yeah, so in my last semester, we had quite an idea of quantum chemistry. So I just wanted to dig in more into this. That's why I joined this course.
But when you have studied quantum chemistry, have you studied quantum chemistry along with some programming?
Oh no, I just did programming on my own. Like I did some online courses and Google Analytical courses for programming. So that was the only source.
But programming in the context of
No, I haven't.
or
I'm
is
just
general programming.
no, general programming. Only general programming.
That is exactly what I have realized, that we are studying, and I have studied in IIT Bombay, and then I have studied in Calcutta University. So when I have studied, quantum chemistry was introduced, but never any programming in the context of quantum chemistry was introduced. And that's why I realized this need. I think there is a need for this. We have tried to give in few Python session, which would be useful to begin with. And I think it is enough to roll the wheel, which you can carry forward very quickly. Okay?
Yes, sure, sir.
Yeah.
So, sir, we were talking about the normalized and normalizable functions. So I'm having difficulty in separating these two things. We were talking that there's a Hilbert space and the function should be inside it and we were discussing about all that. And we said that it should be normalizable. That question you gave us in the assignment too.
So one function which is already normalized, what does it mean? See, quantum mechanics has only one physical interpretation. Okay. There are many ways you can say it, but in a single sentence, I would say that it has only one single physical interpretation. And that is that comes from statistical interpretation. And what is the statistical interpretation? You are actually having probability density distribution over the space. So this by two fingers, I'm showing the space, linear space, let's say. Now, in this space, the distribution function like this, okay? So total distribution from minus infinity to plus infinity over this linear one-dimensional space has to be one, total distribution, because it's a one particle. So the total has to be one, and that's the only interpretation you have. So when you normalize already, that is called normalized wave function. If you do the integration minus infinity to plus infinity, for the density distribution function, it's going to be 1. But if something is not normalized yet, I haven't normalized yet, then this integration has to be a finite positive constant. It cannot be infinite. It has to be a finite positive constant. Okay? Positive constant, it cannot be negative.
So basically, we are saying that when like we're talking about the time dependent thing, but if I make it into a time independent, like I'm not measuring if it's traveling, I'm just considering the particle as stationary. So that particle, if I consider it stationary, then it can only be normalized. Before it can only be normalizable. I mean, it has the ability that it could be normalized when we just start integrating it in the pure surface, in the whole surface.
Right. So, so you have, let me understand it. You have difficulties in thinking about a normalized wave function in the time domain. Is this the problem you have?
So yes, actually, we have just studied about the normalized wave function in the courses till now.
Yeah. So you haven't studied much this Hilbert space. Am I right?
Yes, sir. Yes, it's a purely
That's the
new
problem.
concept.
So basically, how do you normalize it? You normalize it by taking the integration and get some value, and then value you take the square root of that value and then divide it. That's the way you normalize it, right?
Yes, sir.
Okay. So after doing this division, you get a function, right? And that function is called normalized function. And here we are saying that before doing this division, before doing this integration, whether a function can be normalizable or can be normalized, okay? Or is it a normalizable wave function? Can you follow that procedure and normalize the wave function? That's the question we are asking. And answer is yes, I can normalize it, and it would be normalizable wave function if the integration is positive finite value. Getting my point? And if it is normalizable, which means square integrable. Square integrable, what does it mean? It means that you can integrate that one. You do the integration now. So whether it's an integrable or not, all functions are not integrable within a particular limit.
Yes, sir. Yes, sir. You gave us an example.
So that's the basic idea. So before normalizing a wave function can be normalized or cannot be normalized. We don't know. In order to judge whether it can be normalized or not, I have to get that integration to be finite positive constant. Then you can divide square root of that value, right?
Yes, sir.
Okay.
Got it.
The basic idea.
Thank you, sir.
Yeah, think of it, and even after closing this session, today's session, and also the NPTEL entire coursework, if you keep thinking of it, and if you have trouble in understanding certain aspect of quantum dynamics, definitely write to me. I'm available. I'll be able to help you with whatever I know.
Sir, I have one more question, sir. One just.
Yeah, go ahead, Sandeep.
Yes, sir. Sir, it is regarding the wave function, what we selected in case of Bohemian mechanics. There the phase part was also a function of a space as well as time, sir. Yeah. S part we selected, no, sir. And also amplitude part, there also we selected both part. Yeah. So those kind of wave functions, sir, where we can use, sir, because till now we have not used, no, sir, because we have only used that Hamiltonian based time evolution part, sir. That e raised to the power minus h by h cross. That time evolution part only.
That time evolution has nothing to do with this phase.
Yes.
I will do one thing. There is no problem set for the Bohemian mechanics. Is there any problem I have set? Any problem?
No, sir. No, sir.
The help of Bohemian mechanics?
No, sir. No, sir.
No problem has been solved. Okay. So I will do one thing, Sandeep. I will send you one problem, real, what you can solve with the Bohemian mechanics. In fact, you have studied the free particle motion, right?
Yes, sir. Yes,
where a free particle, the wave packet is moving, right, and spreading out. So that idea, problem,
yes,
can be solved with the help of Bohemian mechanics, and you can prove that the center is following, the center of the wave packet is following the center of the wave packet following classical mechanics, right? Similarly, through Bohemian mechanics, be able to do that. So all you need to do is that you have the Gaussian wave packet expression time t, right? That is the very nice expression alpha t, then gamma t.
Yes, sir.
We have given now at a simply Gaussian wave packet. That wave packet has to be converted such a way that the phase becomes real. This S part is real. S has to be real.
Yes.
If you could remember the final expression for the Gaussian wave packet at time t, that wave expression has phase to be complex. Alpha is gamma is complex. We cannot keep that form. We have to again do little mathematical calculation and get the form to be where S is going to be real. Okay, and I'll share this problem with you, and it can be a good idea, Sandeep, if you are very much interested in this. Try to solve all the problems which is coming to your mind with the help of Bohemian mechanics. Okay, a linear potential, let's say, quadratic potential problem, a Gaussian wave packet. So I'll share this problem with you.
Okay, sir. Thank you, sir. Thank you.
Yeah. Is there any other question? So somebody is sitting in the NPTEL office?
Yes, sir.
Yeah, so it seems to me there is no other question. Should we stop the session right now, or?
Yes, sir, we can, sir.
Huh?
Yes, sir, we can wind up the session.
We can end the session. Okay, conclude the session. Okay, because there is no other candidates joined, and it's not a good idea to wait. They can always come back to me. And okay, so we will end the session. I thank Gracie and Sandeep for this session. I really have enjoyed talking to both of you, and then I encourage both of you to think more. Okay, information is given already. Do not memorize. Think and try to visualize all the problems you are dealing with in this subject. I encourage both of you to do that. So we will.
Okay.
We will end the session. And if you have any question, don't hesitate to write to me. I'll be able to get back to you. And we do not need to do this through NPTEL. We can always come online through Google Meet or something else, and we can continue the discussion. Okay.
Okay, sir. Thank you.
Continue the scientific discussion. Okay. Take care. I'll end this session. Bye.
Thank you so much, sir.
Yeah.
Okay,
bye.
Sir. Bye.
Thank you, sir.